Hello friends, we are going through the 80387 numeric data processor. In our last video, we have seen the data types register set supported by 80387. Now, like your 80386, this 80387 also provides some kind of instructions. Today we'll see load and store instruction which are provided by your 80387 processor. In that, real transfer instructions, real transfer, load and store instructions. The first instruction is FLD, that is load real. This F stands for floating point load real. In this 80387 instruction set, every mnemonic or every instruction is preceded with this F. F stands for floating point. The form in which 80387 works internally. This F is a floating point. In this form, your processor works internally. So, what exactly this FLD is? This instruction push the source operand to the TOS. TOS is top of the stack. Push the source operand to the top of the stack. This instruction pushes source operand onto the 80387 TOS register ST by decrementing the stack pointer by 1. ST is your stack top, and then copying the contents of source operand to the top of the stack. Means it simply push the operand to the top of the stack. Here is the syntax for this instruction is like this: FLD and source operand. This source operand then pushed onto the top of the stack. For example, FLD source operand may the long real type, or your source operand may be the short real type. FLD short real. And the exception flag generated during this instruction are interrupt flag and direction flag. Now the second instruction is FST, that is store real. It stores the value in the stack top in destination operand. The syntax for this FST is given here: FST and destination operand. Now the destination operand may be ST3 type, or this may be long real type, or it may be short real type. And the flags generated during this instruction are interrupt flag, user flag, and overflow flag and parity flag. The 4 flags are generated during this store instruction. Moving to the next instruction, that is FSTP, store real and pop. This instruction store the stack top of memory and then pops the stack. Now the syntax for this is given: FSTP, store and then pop, and destination operand. Your destination operand may be short real type, or destination operand may be long real type. That is why FSTP long real, FSTP short real. And the flags generated are interrupt flag, user flag, overflow flag, and parity flag. The next instruction is exchange register instruction, that is F exchange. Again, F stands for your floating point and exchange. This instruction exchanges the destination operand with the top of the stack. If the instruction is used without an operand, the default destination operand is ST of 1. Means there is a condition this instruction may use destination operand or may not use the destination operand. Well, it is not using any destination operand, means no operand is there. Simply the syntax will be like this: fxch. Then the destination operand is considered as st of 1. Stack top will be 1. Or the syntax is like this also: f exchange and destination operand. Again, the destination operand may be of your st of 3, st of 1. And the only one flag is generated during this instruction, that is interrupt flag. Now moving to the next type of instructions, that is integer transfer instructions. In that we are having some instruction, integer transfer instruction. The first is FILD, that is floating point integer load instruction. It is very important. This FILD basically converts the source to temporary real, and after converting it, push it onto the top of the stack. Now this instruction changes the source operand from binary format to temporary real format. Means it converts your source to the temporary real format, binary to real, and then push the result onto the destination operand, that is onto the stack top. The syntax for this is given here: FILD and source operand. Now the source operand may be a word integer type, the source operand may be short integer type, and the flag generated is only the interrupt flag. Now next integer transfer instruction is FIST. Just now we have seen the integer load. Now this is your integer store instruction. This instruction round the top of the stack, round up the top of the stack, and then result will be stored into the destination. Means what? How it operates? This instruction takes the content of TOS, rounds if accordingly RC field, and returns the result to the destination operand. Now the syntax for this is given: FIST destination operand, and the example is like this: FIST and integer word. Integer word, the destination may be of type integer word or it may be of type integer short, and the flags generated during this integer store instruction are interrupt flag and parity flag. Now next integer transfer instruction is FISTP, that is integer store and pop. The name itself denotes it stores something and then pop. First of all, this rounds the top of the stack and the result will be stored to the destination, and then it will pop the top of the stack. 3 steps are there in this integer store and pop. It's like your store instruction, but after storing the result into the destination, it will pop the top of the stack. It operates like this: rounds the contents of the top of the stack in the same way FIST instruction does, right? Like your store instruction, and then stores the result into the destination operand, again like your integer store instruction, and in addition it pops the top of the stack. The syntax for this is like this: FISTP and destination operand. Again, destination operand will be your integer word or integer short, and the exception flag generated during this instruction are no exception flag is generated. Now next type of instruction is packed decimal transfer instructions. In that we are having FBLD instruction. This is packed decimal BCD load. This FBLD converts the BCD to temporary real and then push the result onto the stack. Convert the BCD and then push the result onto the top of the stack. This instruction converts the BCD packed source operand to the temporary real format and then push the changed format onto the stack. It assumes that source operand is within the valid BCD range. Now what is the valid BCD range? That is from 0 to 9. And this FBLD instruction performs no error checking on the source operand to validate the BCD value. The syntax for this is simply FBLD and source operand. For example, FBLD and array. In this 5-byte BCD number from memory location this array to ST. Moving to the next type of instruction, that is arithmetic instructions. Arithmetic instructions are divided into 6 groups. First one is your addition instruction, subtraction instruction, reverse subtraction, multiplication instruction and division instruction. And the last one is other arithmetic instructions. Every group is having some instructions. We'll see one by one. Now in addition instruction group, we are having 3 addition instructions, that is FADD, add real, FADD P, add real and pop, FI add, integer add. These three instructions are included into your addition instruction. Likewise in subtraction instructions, there are 3 subtraction instructions: F sub, subtract real, F sub and P, subtract real and pop, Fi sub, integer subtract. This is your subtraction instructions. And the last type in addition instruction is reverse subtraction. Reverse subtraction is having 3 type of instructions, that is F sub R and destination source. Subtraction reverse, F sub RP, subtraction reverse pop. The syntax for this is like this: destination source. And Fi sub R, F integer subtract and reverse. And the syntax is like this: source, only source operand is there. This is your addition instructions. Now the next group of instruction is multiplication instruction. Again, this is very important point. In multiplication instruction, we are having some instructions. The first one is FMUL, that is floating point multiply real instruction. It simply multiply the destination by source and the result is given to the destination. As usual, as we have seen in 80386, the IMUL instruction multiplies the source by destination and the result will be stored into your destination like this. And the operation for this instruction multiplies the destination operand by source operand and stores the result back into the destination operand. If this FMUL is used without any specified operand, ST of 1 and ST respectively are implied like this. Syntax for this FMUL is FMUL and no operand, or it can be FMUL source operand, or it can be in the form f mul destination operand comma source operand. And the example for this is given here. When there is no operand, the f mul will be like st comma st1. If there is only source operand, f mul, that source operand can be of this type, and destination and source, the f mul and the destination source can be of real long type and real short type. The exception flags generated during these instructions are interrupt flag, direction flag, user flag, parity flag and overflow flag. Now the next multiplication instruction is f mul p, that is floating point multiply real and pop. This is similar as your addition instruction, store and pop, load and pop. This is multiply and pop. It multiplies the destination by source and the result will be stored at the destination. Only the difference is that it will pop the result or pop the top of the stack. Basically this instruction gets the source operand from top of the stack register stack. Syntax for this is like this: f multiple p, destination operand and source operand. Again, for example, f mul p st4 comma st. Here st, top of the stack 4, that is your destination operand and st is your source operand. And the exception flags for this is interrupt flag, direction flag, user flag, overflow flag and parity flag. And the last multiplication instruction is fi mul, that is integer multiply instruction. In this instruction, it multiplies the destination by source, store the result to the destination. And syntax is like this: fi mul and source operand. For example, fi mul source operand data 3, this can be a source operand. And the exception flags for this: interrupt flag, direction flag, parity flag and overflow flag. The last type of instruction, that is division instruction. Like multiplication instruction, we are having division instruction. First division instruction is fdiv, that is divide real. This fdiv divides the destination by source and stores the result to the destination. Likewise, your multiplication instruction, if this instruction is used without a source or destination operand, then st1 and st are assumed respectively. If there is no source operand, then top of the stack are assumed. The instruction uses st for source operand and st1 for the destination operand, and then it pops the stack and return the result to the stack top. The syntax for this fdiv is: when fdiv with no operand, fdiv with source operand, fdiv with destination operand and source operand. And the examples are given here. Now the next division instruction is fdiv p, divide real and pop. This fdiv divides the destination by source and pops the stack. In this instruction, it takes the st for the source operand and st1 for the destination operand. And next, it pops the top of the stack and perform the division, and finally returns the result to the st1 one register. The syntax for this is given over here. FDIVP, destination operand and source operand. For example, ST can be your destination operand and ST3 can be your source operand, and the result of this division will be stored onto the ST, that is destination operand. And the flags for this FDIVP, that is interrupt, direction, overflow, user, zero flag and parity flag. Now next division instruction is FIDIV, that means integer divide, floating point integer divide instruction. It also divides the destination by source and the result is stored to the destination. The syntax for this FDIV is given. FIDIV source operand. For example, this source operand can be of integer word type or it can be of integer short type, and the flags generated for this are interrupt flag, direction flag, overflow flag, user flag, parity flag and zero flag. This is all about addition, subtraction, multiplication and division instruction. Now the next group of instruction is compare group. Again, this is important as your exam point of view. The comparison instructions compare the data at the top of the stack, that means TOS, in relation to another element and return the result of comparison in the status register. Condition code bits. Now compare instructions are divided into many types. The first one is your COM, that is compare real. FCOM, that is compare real and pop. FCOMP, that is compare real and pop twice. Next is F1COM, that is integer compare. Then FTST, that is test. FXAM, that is examine. We will see every instruction, every compare instruction one by one. The first one is your COM, that is compare real. It simply compares the top of the stack to the source operand, and it operates like it takes the current top of the stack and compares it with the source. And the operand, that means the source, if instruction is executed without a specified operand, the ST1 is assumed. Likewise, in multiplication instruction, if there is no operand, we are considering ST1 as the source operand. The source operand may be registered on the stack or memory location. The syntax for this comp instruction is like this. FCOM, no operand. No operand means ST1 will be considered as your source operand, or syntax may be like this. FCOM source operand. For example, FCOM, this is simply for the no operand, and FCOM real long, this real long is your source operand here. And the flags generated during this COM instructions are interrupt flag and direction flag. Next compare instruction is FCOMP, that means compare real and pop. It compares the source and top of the stack and pops the top of the stack. Simply it compares and then pop. This instruction takes the current top of the stack, compares it with the source operand and then pops the top of the stack. If this FCOM can be used with the without source operand and with source operand, like COM instruction. If this FCOM is used without specified source operand, then ST1 stack top 1 is assumed. The syntax is like this: FCOM with no operand, FCOM with source operand. For example, fcomp with no operand means st1 is considered. And when fcomp real long, that is real long is the source operand. Likewise, fcomp real short. And the flags generated are interrupt flag and direction flag. Next compare instruction is fcomp and p. Compare real and pop twice. Fcomp pp, pop twice. In this instruction, it compares the top of the stack and st1 pops the stack twice. 2 times it pops the stack. The syntax for this is given fcomp pp with no operand. For example, fcomp pp. Now, again with no operand means st1 will be considered as the source operand. And the exception flags are interrupt flag and direction flag. Now next is ficomp, that is integer compare. It simply compares the top of the stack and source. This instruction converts the source operand to temporary real and compares the top of the stack to it. Now the syntax for this is given like ficomp source operand. For example, source ficomp and source operand will be like your integer word and integer short. And the exception flags are interrupt flag and direction flag. Next compare instruction is f1 comp, that is integer compare and pop. This instruction compares top of the stack and source pops the top of the stack. It is same as your previous instruction. In addition, it performs popping of the stack top. For example, this ficomp integer word, ficomp integer short. Integer word and integer short are your source operand. And the flags for this instruction are interrupt flag and direction flag. Now next is FIST, that is test. It compares the top of the stack and set condition codes. It operates like this instruction compares content of the top of the stack register ST with 0, 0. The syntax for this is FIST and with no operand. And the flags generated for this test instruction are interrupt flag and direction flag. And the last instruction is examine, fexam. It sets the condition codes of status word on exam. This instruction examines the content of the top of the stack and register ST. The syntax for this is simply fexam, and the example is fexam with no operand. And the flag generated is none. No flag is generated. No exception flag is generated during this examine instruction. In this way, we have seen the different types of instruction supported by your 80387 processor. Thank you.